So, here you have your metal semiconductor junction, okay, so that is my n type semiconductor, and I have applied a voltage VA, and the voltage is applied such that you see the ground or the reference is kept at the semiconductor, the positive sign is sitting at the metal. So, when VA is greater than 0, it implies that the potential at the metal is greater than the potential in the bulk of the semiconductor. So, that is what we mean by this circuit configuration, right. Now, we will call VA being greater than 0 as forward bias. Okay. Now, you might have all heard this this term in context of diodes, and in fact the Schottky junction does behave like a diode. So, that is why although we have not formally discussed diodes, I am pretty if the students have heard of diodes before, then you might have heard the term forward bias in the context of diodes. But nevertheless, let us just go ahead and call this condition as forward bias, okay. And when VA is less than 0, it is something called as reverse bias, okay. So, now what happens to the band diagram when I apply a potential? So, let us look at these pictures here. So, this is the condition of equilibrium. So, this is the equilibrium condition that we are very familiar with, and on which we performed all the electrostatics analysis, right. So, that is my conduction band edge, that is the valence band edge, that is the Fermi level, that is the built in potential that we calculated out, and that is the depletion region which has got a depletion width of xd, okay. And that was the relation between, so xd turned out to be square root of 2 epsilon s phi bi by q n d. Okay. So, that was the relation that we obtained. Now, the moment you take it out of equilibrium by applying a bias, by applying a potential VA, what happens is you start, the Fermi level need not be aligned anymore. You are now creating, you are trying to change the flux. Now, why did the Fermi level align? So, if you remember the calculations when we looked at the fundamentals of junctions, we said that the Fermi levels aligned because the flux of carriers from the left to right across the junction was the same as the flux of carriers from right to left, and that is true only at thermal equilibrium, right. Now, the moment you take it out of thermal equilibrium, but the moment you apply a bias voltage, you are attempting to favor one direction as compared to the others. Now, when you apply a forward bias, when your VA is greater than 0, the Fermi level of these semiconductor is now split away from the Fermi level of the metal. The two Fermi levels are no longer aligned, and you have to split away by the amount of voltage you applied, and since we are showing everything in terms of energy, it is Q into VA. Now, because of this, the built in potential changes, okay. So, the built in potential is no longer Q phi bi, the built in potential too is lowered by an amount of by the same amount, that is VA. So, essentially what this means is that if you look at this picture here on the left hand side, the bottom left, so that is my equilibrium condition when my VA was 0. So, we are looking at only the conduction band, okay. So, we are trying to compare, put these two plots on the same figure here. So, that is my conduction band at VA equal to 0. The moment we apply VA to be greater than 0, the band bending becomes a little bit more gentle, okay. So, this bending becomes a little bit more gentle, and the built in potential goes less than the built in potential at equilibrium, okay. So, that is what happens in forward bias. But note what has happened to the barrier height. The barrier height remains unchanged, and why is it? Because the barrier height, okay, if you think about it, let us say there is the vacuum level there, okay, that is the vacuum level, this is the electron affinity. So, as we if you mark it from the semiconductor side, that is the electron affinity of the semiconductor, and from the metal side, just if you just slip it down to the metal side, that is the work function of the metal, and both these are material properties that are constant, and therefore, this barrier height is essentially q times phi m minus chi s. Okay. And therefore, that the barrier height remains unchanged. Okay. So, you are not influencing the barrier height in any manner. So, the barrier height remains the same, it is only the bending of the bands that becomes more shallow. Now, when you apply reverse bias, the opposite happens. The work function of the the Fermi level of the semiconductor now lies below the Fermi level of the metal. So, by applying a positive voltage by applying a negative voltage to the metal, we have in fact made the metal Fermi level go higher as compared to the Fermi level of the semiconductor, and therefore, the bands now bend a little bit more steeper. Okay. And you should remember that Va is negative. So, that is why Q into phi Bi minus Va is actually going to be greater in reverse bias as compared to equilibrium. Okay, so, Va is less than 0 in this case Va was greater than 0. Sorry, I should have labeled that. I just realized that these labels are missing. So, that is the case of Va greater than 0, this is the case of Va less than 0, and that is the case of Va equal to 0. So, this case corresponds to this drawing here, that is in black. This case corresponds to this drawing here, that is in blue, and this case corresponds to this drawing here, that is in red. So, now let us look at what happens to the depletion width. At equilibrium, the depletion width was simply given by this term, but Va being equal to 0, there was no Va. So, that was the depletion width. This is what we had calculated from the solution of Poisson's equation. Now, after we apply a bias, the depletion width changes to having a term of phi Bi minus Va inside. When Va is greater than 0, that is when you are in forward bias, the depletion width goes smaller, because phi Bi minus Va is going to be smaller as compared to phi Bi, and the depletion width is now less than the equilibrium depletion width. And when the device is reverse biased, phi Bi minus Va is now greater than phi Bi, and the depletion width goes to be greater than the equilibrium depletion width. Okay. So, therefore, the depletion width of the device in forward bias is smaller than the depletion width of the device in reverse bias, with the depletion width and equilibrium lying in between these two conditions. Okay. So, now let us look at the capacitance of this junction. Okay. So, we are trying to head towards the calculation of the effective small signal impedance, right. So, we want to know what happens, what if I have a Schottky junction, what impedance does it offer when I apply a voltage across this, and what is the kind of current I would get across. Okay. So, capacitance is one of the aspects of the impedance calculations. So, what is a capacitance? So, if you think about the Schottky junction, you have metal on one side, then you have a depletion region here, and you have a N type semiconductor here. So, the N type semiconductor, the bulk, can be thought of as a resistor, which is what we have looked at when we studied the mobility of carriers in types. The metal also is a very low resistance resistor. The depletion region of, however, has got space charge, right. It's got just these fixed ions. It's got no mobile carriers. So, there are no electrons, I should not say no mobile carriers, it's got very few mobile carriers. Okay. So, these two are negligible. So, it is as though you have these two resistors and there is a kind of a depleted or non conducting insulator in the middle. So, one can imagine it to be that way. So, therefore, this is like a capacitor, okay, in some sense. And what we would like to do now is to calculate the capacitance of this capacitor. Now, if you think about this in this manner, the capacitance of what we need to calculate is the capacitance of the parallel plate capacitor, right. So, the device had some cross section area A, okay. This is equivalent to having a capacitor which has got two plates with cross section area A with a insulator in the middle which has got a thickness of xd, which is the depletion width. So, what is the capacitance? It is going to be epsilon s A by xd, that is going to be the total capacitance of this junction. But if we want the per unit area capacitance, okay, so we are interested in finding the per unit area depletion capacitance, capacitance of the depletion region. So, per unit area implies I will just remove the A term there and just have epsilon s by xd. Now, I know my xd is this and I divide epsilon s by xd in order to get this to be the capacitance of the depletion region. Now, this may not be the most general method of thinking of capacitance, okay. So, it worked out very nicely here because we could draw a nice analogy to a parallel plate capacitor. But from henceforth it would be good to think of the capacitance across two terminals in a slightly different manner, and let me describe that, okay. So, what we want to calculate is something called as the small signal capacitance, okay. Now, what do we mean by that? So, let us say there is some device that is sitting inside a black box, okay, and you have these two terminals across, okay, and we want to measure the small signal capacitance, small signal capacitance. Now, what is a capacitance? How do you define capacitance? Capacitance is, so suppose you had your familiar parallel plate capacitor and you were to apply a voltage V across this capacitor, you will store a charge Q on this capacitor and your capacitance of this capacitor is Q by V. So, it is the amount of charge stored on the capacitor for a given voltage V. Now, what we mean by small signal capacitance is this: we now apply a small fluctuating signal, okay. We will apply a small AC signal. So, let us say it is a tiny fluctuating sine wave, if you like, at some frequency omega. So, essentially it is going to be the input that we are going to give to the circuit is going to be, say, some V naught sine of, let me just write it a little bigger, it is going to be V is equal to V naught sine of omega t. Okay, so, let us say we are giving a small, this is a very small signal, and what you mean by small is a great question. It simply means that it is small enough that the device can be considered to be linear, okay, and we will understand these concepts a little better as we go down. So, now if I were to apply a small voltage fluctuation here, this device has got some charge, okay, it is all, we cannot see it, but we can sort of measure it, okay. And this charge is going to fluctuate in response to this applied voltage. So, because of this applied voltage, you are going to see an effective fluctuation in the charge inside the device, okay. So, that is dV applied and that is the dQ, the fluctuation in the charge, and we know what we are applying here and we can measure this fluctuation, and therefore, the small signal capacitance is simply dQ by dV, and in our case, since the depletion capacitance is dQd by dVA. So, if you were to perform the same experiment on your Schottky junction, so you have that to be the junction, this is the depletion region and that was xd, right, and we already know that xd is a function of the applied voltage. It varies, it is proportional to square root of phi bi minus Va, and this region has got all the positively charged donors, right, it has got some charge that is balancing any charge that is applied on the other side. Now if I were to fluctuate VA, so let us say I set a certain bias value for VA, and then on top of that DC bias we are going to fluctuate VA a little, okay, we are going to have a small fluctuation in VA. So how would the depletion region respond? The depletion region will respond by changing the position of XD, right. So this position, the XD is going to fluctuate, it is going to move up and down. Let us say we are doing these measurements in reverse bias. So VA is less than 0 and then you are having the small signal fluctuation here. So as VA goes a little higher, XD reduces a bit, and if VA goes a little lower, XD increases a bit, okay. So therefore as VA fluctuates, your XD fluctuates. So essentially it covers and uncovers either more or less, it exposes more donor charges, fixed ions when VA goes up, and it covers up some of the donor charges when VA goes down. So by fluctuating XD you expose and cover up these donor charges, and therefore it is a response of charge to the applied voltage. So that is how your Schottky diode behaves, in the Schottky contact behaves in response to the a small signal variation in the applied voltage. So your dQd by dVA is essentially your capacitance, and you will find that if you were to perform this calculation, you have XD as a function of VA, you take a differentiate this with respect to VA, you will find that you end up with the same expression as our little picture of a parallel plate capacitor. Henceforth it is more useful to use this approach to calculate capacitance, because it is a more generic approach, it is a approach that is compatible with performing an experimental measurement, okay. So we will keep this in mind, and whenever we discuss the other devices, let us say a PN junction diode or any transistor, we will use this approach to calculate or measure what the capacitance is. If you look at the capacitance, the expression for the capacitance, okay, so C is given by this term here. So if I were to plot, if I were to take 1 by C square, okay, what is that? 1 by C square is nothing but 2 into phi bi minus VA by Q ND epsilon s. So if I were to plot 1 by C square as a function of VA when VA is negative, okay. So there is a reason why I am picking reverse bias, because in forward bias we are going to see soon that we are going to have other aspects of the impedance coming up, because you are going to have currents, significant currents. So if you were to perform a measurement where you plot 1 by C square versus VA, so you measure, you take an experimental setup and you go ahead, put your device through the setup, measure the capacitance for different negative biases, okay. You are going to set VA as -1 volt, apply a small signal, measure the capacitance and mark a point, set VA as -2 volts, perform a measurement, mark another point, and do this for several negative biases, and you will end up with a, you should end up with a straight line, because 1 by C square is linearly related to VA. So this is a straight line, and the slope of the straight line has to be -2 by Q ND epsilon s. So therefore if I know my, if I have my capacitance measurement, if I have this measurement, if I have this experimental result, I can extract what my ND is, okay. So even though ND was decided at the time of fabricating your device, we can measure out what ND is. So it is a useful point to remember. So now let us look at the current voltage characteristics through a Schottky contact. So we have seen that by applying a bias voltage to the metal semiconductor junction, we can change, we can alter the band bending by varying your applied voltage VA. So when VA is greater than 0, the band bending becomes more gentle, Okay. So, the band bending is gentle, and when Va is less than 0, the band bending gets more steep, okay, as compared to the equilibrium value. So, equilibrium lies somewhere in the middle, we just call that as band bending is normal. So, because of this change in the bands, I mean the band structure, we are going to see some mechanism, we are going to see things move out of equilibrium, okay, and this essentially is going to lead to the effective change in the effective flux of carriers across the junction, which implies that we are going to start seeing charge moving in one particular direction as compared more charge moving in one particular direction as compared to the other, and therefore we are going to see currents across the junction. So, we are interested in looking at the current voltage characteristics in a Schottky contact. We are still talking about Schottky contacts. Okay. So, metal semiconductor contacts had two kinds, there were Schottky contacts and ohmic contacts. We are still talking about Schottky contacts. We looked at the electrostatics, we looked at the non-equilibrium case, we have looked at the measurement of capacitance, and now we are looking at the current voltage characteristics. So, there are three general mechanisms, okay, for current that lead to currents in a Schottky contact. Okay. Now, the first two mechanisms are in some sense, the general behavior is quite similar, but although they imply a slightly different physics, okay, and they are called as diffusion and thermionic emission, okay, and they are both represented by this arrow here. Okay. So, this arrow represents both these ideas, okay, and I will explain what those are. And the third mechanism is something that we have looked at when we studied quantum mechanics, and it is called tunneling. Okay. So, what are diffusion and thermionic emission? Okay, now this is what happens. Okay. So, you have your some electron population here. So, let us say this region is all depleted. Now, these electrons are at equilibrium, these electrons are trying to diffuse over to the other side. And what do you mean by diffusion? You have a barrier, okay, there is a concentration gradient here, and this concentration gradient is driving this current across this junction, but that current is balanced at equilibrium. That current was balanced by carriers that are moving across from the metal to the semiconductor. Okay, you have an equal and opposite flux from the metal to the semiconductor. Now, this concentration gradient, okay, this dN by dx is very dependent upon the built-in potential. And why is that? It is because the electrons all have a Boltzmann's distribution. So, they all vary as they are all proportional to your e to the power minus qbi by kt. Okay. So, as the built-in potential changes, your electron concentration would be affected. Okay. And in case you are wondering how this came about, you can you go back to the general study. I am just going to go back a few slides. Okay. So, you can see that in this expression here, okay, this is where we sort of wrote out all the quantities for your exact solution of Poisson's equation. So, I am going back a few slides because it is illustrative, and you can see that the carrier count depends upon all these potentials. Okay. So, the built-in potential plays a role in the carrier count. So, now if I change the built-in potential, I therefore can influence the carrier count, okay, and I can therefore influence the carrier concentration, and that can lead to an effective diffusion current. So, that is the diffusion current mechanism, okay, and we will look at it in more detail. So, essentially it is the diffusion of the carriers that have got a count of e to the power minus q phi by kt. So, it is this effective number that is going to create the concentration gradient. that is diffusion. So, diffusion very strongly depends upon the nature of the band bending and what the built in potential is and what the shape of this bending is, etc. So, it is very dependent upon all these features. Okay. So, that is diffusion. Now, thermionic emission is a little different. Okay. So, what thermionic emission says is that irrespective of what this band bending looks like, okay, we really do not care about the band bending. We only know that the barrier that we need to cross from the semiconductor to the metal side, we have to cross this barrier, and from the metal to the semiconductor side we have to cross that barrier, and we only look at those electrons that have got a large enough energy and large enough velocity. Okay. Basically, if you think about it, the electrons sitting here, let us take an electron at the conduction band edge. It has just climbed up from the valence band to the conduction band and it has got 0 velocity. Okay. Now, as the electron climbs in energy, its velocity increases, okay, and after it crosses this particular line here, its velocity is increased to such an extent that its kinetic energy, okay, the kinetic energy of the electron is now greater than say phi bi or phi bi minus Va, if you are talking about this in a very general sense. So, these electrons have got enough energy, they are sitting here, okay, they have got large enough velocity, these electrons are located there, they really do not worry about the barrier, okay, they do not really worry about the band bending. Now, this electron has got so much of energy, and if you just measure the effective flux in one direction, it is the current contribution of that electron. Okay. So, thermionic emission takes a look at all the electrons that have got a velocity large enough, that has got a high enough energy that can simply walk past the barrier like as though there was no barrier existing there. Okay. So, we just see how the flux from right to left is affected by the applied voltage and how the flux from left to right is affected by the applied voltage, and the effective flux is the difference of these two. And if that effective flux is affected by the applied voltage, then definitely you will have a current, and that current is something called as thermionic emission. Okay. Finally, tunneling is quite different. So, in the case of tunneling, even though there is a barrier, okay, despite the presence of a barrier, you have electrons sitting here, they do not have enough energy to walk over the barrier, but they can definitely tunnel through this barrier. Okay. So, the electrons actually, the wave function, the probability of finding the electron on the other side of the barrier is non-zero. Okay. So, we are familiar with looking at rectangular barriers. So, when we looked at quantum mechanics, when we said particle in a box, we said it was really a box. So, we drew diagrams like this, the potential energy diagram looked like this, with the electron having a sinusoidal wave function here and then an exponential decay in the wave function outside the box, and that was the barrier we always discussed. But here the barrier, if you think about this band diagram, the barrier is not a rectangle. Okay. It has got this little it has got a straight edge on one side and this quadratic appearance on the other side. Okay. So, these are the three mechanisms that we will discuss: the diffusion, the thermionic emission and the tunneling. Okay. And what we are going to do now is go through a lot of mathematics, okay, and calculate out what the current due to diffusion is, what the current due to thermionic emission is, and what the current due to tunneling is. Okay. So, once again, please do bear with me. I understand that lecturing on a lot of equations may not be the most interesting thing to do, but nevertheless it is important that you know how to calculate and see where all these how to put down this physics and this concept and chalk out the equations required for calculating these currents. Okay. But as I mentioned, you will not be quizzed on, nobody is going to ask you to derive these different aspects in your tests and exams. Okay. The exams will be purely based on your understanding and concepts.